Okay, so yesterday we reformulated the Pentagon equation in terms of the triangular prism equation. So the idea was to start from the usual Pentagon equation as written here, and then to reformulate every F symbol here with our monoidal tetrahedron as it was explained here. So we are reduced to an equality of monoidal tetrahedron, which can be reformulated pictorially like that. So then it remains to make some move and some modification on this equation to recover the exact labeling for the reference pattern of the TP. This is what we did up to here. It remains a few. So we are almost done here. It remains a few orientation which should be changed to have the exact shape of the triangular prism equation. So finally, by adjusting the orientation and to adjust the orientation as we want, we will use a natural transformation sigma I, generalizing the natural transformation sigma. So I will explain. So by adjusting the orientation using the natural isomorphism sigma I equal 1, 2, 3. So I will explain what are these natural transformations defined as for sigma, but for the his leg. So I will draw a picture. And remember, sigma corresponds to the third leg. We recover the triangular prism equation from theorem 810. So let me explain. So then we will state the change of basis. We can state the change of basis between PE and TPE. But before that, let me explain. Let me draw the picture for sigma 1 and sigma 2. Sigma 1 of alpha is like that. So the first leg here is AX, X, Y, Z. Sigma 2 of alpha is like that. So the second leg. And sigma 3 is exactly sigma as defined before. Okay. Okay. So we can state the change of basis. In fact, all this discussion here is the proof of the change of basis. theorem. So PE, TPE, change of basis. So we'll take the assumption of theorem 8.10. So remember this assumption. We have, if I remember correctly, we have x double star equal x and ax square equal identity or something like that. Under the assumption, plus sphericality also. Under the assumption of theorem 8.10, so this is what we call the simplified TPE, if I remember. Its triangular prism equation is exactly the Pentagon equation, the one we called 14, the equation 14, which was recalled here. Here. So the TP is exactly that, up to a change of basis. I will right now under the following change of basis. So here is a change of basis. So the change of basis looks like that. So you have, remember that you have morphism alpha I with I equal 1, 2, 3, 4, 5, 6. You have morphism beta 0, beta 1, beta 2, etc. And you have object x1, x2, etc. So we will write the proper change of basis to go from one to the other. Here, so in theorem 8.10, you have the notation I just mentioned. Here we have this other notation, mu, etc. So we will explain how to go from one to the other. So alpha 1 is rho of mu. This is not mu. I forgot. mu3 tilde right dual. Alpha 2 is rho 1 inverse. So sigma 1 inverse. Sigma is the one we just, the natural transformation we just defined here. Of mu1 tilde right dual. Alpha 3 is etc. etc. So it's I hope I am not making a mistake somewhere, but this is exactly how this change of basis looks like. So it's interesting to see this change of basis. This tells us that TP and P, so they are equivalent up to a change of basis. They are equal up to a change of basis, but they are not equal without any change of basis of that. It's a different point of view. So this is an important thing to understand. So TPE is another point of view of the Pentagon equation. And this other point of view may be relevant for some application. So here I just write the change of basis as it is written in the paper. So in fact here, I assumed 1, 2, 3, how many parentheses? 4. So as you can see here, I assumed this part by adjusting the orientation. So I hide, in some sense, an extra picture like that, where we made the adjustment and where we have to add all this natural transformation. But yeah, so if you like, there is an extra picture like that where you have the exact orientation, and then you get that. But yeah, it's okay. I omitted this part. And alpha 6 is sigma 1 rho of like that. So this is for alpha 1 up to alpha 6. Now you have also beta 0, beta 1, beta 2, beta 3 in theorem 810. So what about that? You have beta 0 equal like that. Beta 1 equal rho inverse of mu 9 tilde radial. Beta 2 equal rho inverse of mu 7. I hope I am not mistaken while by writing that. But in fact, so I don't know if the full details of this change of basis matter or not. What matter is the existence of such change of basis. So we know that the TPE is really PE. So a solution, you have a solution of the TPE. If only you have a solution of PE, considered as a full system. Thanks to this theorem. So this is what we will need for application, for example, for near group. We need to show that if you find a solution of the TP, then you can categorify. So a priori, so as far as I know, the details of the change of basis does not matter. You just need to know it exists. So even if I make a mistake somewhere in some indices, it does not matter. As far as I understand the thing. Anyway. So this is for beta 0. Now, the object, so xi0 is x, x1 is xi3 star, etc., etc. x2 is xi1, x3 is xi2, x4. So it's a change of basis. So yeah, it may not be completely the notation. It's an abuse of notation here. But there may be some conflict in the notation because, for example, I don't know, I1 can be something. So it's not an equal. It's just you change the basis. So I don't know how to say. You should make an error. This is just a change of basis. Okay. Then x5 equal xi4, x6 xi5 star, x7 xi9 star, x8 xi7, x9 xi8. Okay, so you see it's quite interesting. We can write explicitly this change of basis, so it's very technical, but it's not so complicated. And as I said, only the existence of this change of basis matter. Okay. In fact, this change of basis can be depicted as a new labeling of the TP, and this new labeling will be called the PE configuration. The change of basis in previous theorem can be depicted as a TP with a specific and in fact specific. What is interesting in this specific TP is that you can you can make the good you can put the good corner and the good orientation in such a way that every natural transformation disappears. So you will have an easy picture realizing this change of basis. So it is beautiful. So specific PE with a specific PE configuration. See coming. So it's figure 3 we will write. So let me specify that we rotate. So you have remember that the TP can be realized in 3 dimensions, and then it is invariant by 3D move. And the TP we wrote here in figure 3, I will write here in figure 3 is rotated to match with the reference pattern figure 1. So it's which is rotated for a better matching with the figure 1. So remember the figure 1, which was close to the theorem 810. So I will not copy the figure 1 here because it's too far. But anyway, so theorem 810, so it's in section 8. So here is a figure. The PE configuration is the following. Okay. So orientation, like that, like that, like that. So it don't worry, it will be very quick. Like that, and like that. And so let me write so we can write the morphism without any natural transformation. Like that, because we choose a good corner here. And what is very funny here is that so the usual TP, so the reference pattern, is much more symmetric. The labeling is much more symmetric than the PE configuration. And so it's funny that we get something which is a little bit less symmetric. So which may, sorry, let me take another color. which mean that for such pictorial representations, the TPE, the reference pattern we choose before, is more relevant than the one coming from Pentagon equation. I7 star, I9, I8 star, I3, I2, I1 star. Okay. So this is figure 3. PE configuration. Okay. So if you remember, the usual TP configuration labeling was, it looked like that, but with some difference. I don't remember. I don't remember. Maybe both are inside here and here. I don't remember. Go to the section 8. It was a little bit more symmetric. Here you see, here it's here, 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 etc. Okay. So maybe I can try to look in the paper if I want to see the previous. Maybe I can go quickly by. I guess I am referring to this one, triangular prism configuration. Figure 1, yeah. So I will copy and paste that, and it will be more. Oh, sorry. Okay. Then I need to come back to section 13. Here. Okay. I will put the figure 1 here, then we can compare directly the two. Let me write it here. Figure 1 from section 8. Okay. So you see, yeah. This is our reference pattern coming from the triangular prism equation can be this represents the triangular prism equation. This represents the Pentagon equation. And you see, it was much more symmetric. You have here, 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 here. So it was much better. Same orientation here. And like that. Here it's different. You don't have this. Yeah. Maybe there is a way to make this more symmetric. I don't have. But it cannot be the same because otherwise it would be an equality, not up to a change of basis. So there is a subtle difference between these two configurations. And this subtle difference is represented by this change of corner and this change of orientation. But from this point of view, this configuration is better. It's much better. Much more symmetric. Okay. Okay. Let me just put this in some. Oh. What? Pourquoi ça ne prend pas? Oh, I don't. Anyway, I will keep it like that. Okay, so now I will explain. So I will mention some reference to explain that. So solving. So as we said, Pentagon equation and triangular prism equation are equivalent. So now we need to explain why a solution of the Pentagon equation provide a categorification. So we will cite a paper by Davidovich, Haag, and Wang. More precisely, the proposition 3.7, where they discuss the Pentagon equation and categorification. And we will also explain that, so then, according to the previous theorem, a solution of the Pentagon equation of the triangular prism equation provides the categorification by this result, Davidovich, Haag, Wang. But we should check the sphericality, because it's an open problem whether every fusion category admits a spherical structure. So if you find a solution, we need to check also that this solution is spherical. A priori, it's not automatic. We use sphericality to depict, to simplify our equation. But yeah, it's not clear to me that a solution of an equation will provide a spherical categorification. We will need to check also sphericality. So let me write this. It will be a big paragraph. So let F be, so I finished that. Let F be a fusion ring with basis Bi, I in I, and fusion coefficient. Yeah. So in okay. So in section 10, so section 10, we use the TPE as a criterion to exclude. But if you want to categorify, as I said, we need more. To exclude, there is no problem. We don't need to prove the equivalence with Pentagon equation, because you can generate this equation from in the categorical framework. So in section 10, we employ the TPE equal Triangular Prism Equations to establish criteria for the categorification of F. Okay. Now, so criteria mean a necessary condition, not necessary. This necessary condition is not sufficient. This necessary condition, if it is not satisfied, can be used to exclude F from categorification. Now, if you want to categorify, now applying the result of theorem 12.2 And as I said, so term 12.2, PE is the same as TPE up to a change of basis. And now, for PE, you have the result of Davidovich, the paper Davidovich, Hag, Wang, 2013, and you should consider the proposition 3.7. So this is for TP equal P up to change of basis. This is for PE. Solution of PE imply categorification. So with these two results, we get that the TPE can indeed be used to categorify F. And what we need is a sphericality, assuming it is the Grothendieck ring of a spherical fusion category. It is the Grothendieck ring of a spherical fusion category. Okay. So now I will explain. We need, even if you find a solution of the TPE, we will need to check the sphericality. So it is important to note that the proof of theorem 12.2 hinges on the property of sphericality. Therefore, the categorification require not, okay, so for the categorification, you need to check all the TPE, all the TPE. So you have all the system of triangular prism equation. You need a solution. If you have a solution, you need this solution should satisfy every equation. But it's not enough to check. For the categorification, it's not enough to check all the equations. You also need to verify the sphericality. Therefore, the categorification require not only to the verification of all TPE. So I choose to do not put a S. So there may be a confusion when I say TPE as a single equation or TPE as a full system. But the context, you can understand if it is single or full with the context. Maybe I should think about that. But here it's a full system. So all TPE, but also additional assumption to ensure sphericality. But yeah, it should not be too hard, in fact. to check sphericality. The point is that we already applied this system to a paper for the multiplicity-free up to rank 6. So we apply our simplified TPE for the multiplicity-free, multiplicity 1. And then we can always find unitary solution. So in fact, unitary is automatically spherical. So maybe this text is too long for something which is not so hard. And as we will say, as we mentioned before, in fact, sphericality is just that dimension of x equal dimension of x star for all simple object x. So yeah, it should be very easy. If you have a solution of the Pentagon equation, it should not be so hard to check the sphericality, but in fact, I realize that in fact, maybe this text is useless because we already assume that the dimension of x equal dimension of x star, because we start from the fusion ring, and I guess in a fusion ring you already have the Frobenius per. So if it is pseudo-unitary, there is no problem. But I guess this method is pseudo-unitary. So anyway, because you start from the fusion ring and you consider the dimension of the Frobenius per dimension of the fusion coming from the fusion ring. And for the Frobenius per dimension, you have the Frobenius per dimension of x equal Frobenius per dimension of x star. So it's automatically spherical if you have a pseudo-unitary categorification. So no, maybe we don't. Maybe what we did in this work, do not assume pseudo-unitary, because you can consider any character. So the dimension, at least in the dimension is a character. So we can consider any character as a categorical dimension. And then if you write the equation like that, we will have we will need sphericality anyway. So you have to be careful about sphericality. Anyway. Okay, so now what I want to say. So now I want to write the pivotal structure pictorially under the assumption in theorem 810. So the TP. So the TP, the triangular prism are considered up to. So before talking about pivotal structure, I just say that the TP are considered up to A4 symmetry, and this A4 symmetry was proved using sphericality. So they are spherically invariant. So the TP are considered. So I will have to update this paragraph, which is too long for something that may not be required. Such a long paragraph. So these TP are considered up to A4 symmetry, meaning they are spherically invariant. So this is something we explain in full details in some previous section. Now, about the pivotal structure. Recall that if ax double star equal x and ax square equal identity of x as assumed in the theorem 810, then AX is plus or minus identity of X. So that we explained that before. Thus, so the pivotal structure is given by a sign. We define epsilon I to be plus or minus 1 for each I in I. So big I, capital I is a set of indices for the simple object. To represent the pivotal structure. To represent the pivotal structure. Ensuring that AXI equal epsilon I, identity of xi, so the sign. And that epsilon I star equal epsilon I. So, in accordance with some previous lemma and the paper of Davidovich, Hag, Wang. So there is in this paper, there is an equation 35 which involves this way of representing the pivotal structure. In accordance with, so our lemma 2.6, which is something as AX star equal AX star inverse, etc. So something like that. And the Davidovich Hag Wang equation 35. So you have to go to this paper. So you check. I guess they wrote a single paper in 2013. Maybe they wrote a single paper for this author anyway. And here you go to this proposition and to this equation. In this equation, there is this epsilon representing the pivotal structure. Regarding TP. So, consequently, we have, so you can go, remember you have the evaluation map plus or minus, so you can go from one to the other using this epsilon I. Evaluation map xi plus or minus equal epsilon I evaluation map xi minus plus. So be careful, this is true under this assumption. You cannot say in general, you can write that. No, under this assumption only. And I will draw a picture for that after the pause. So pause. And we will finish this section after the pause. It remains only one paragraph, one small paragraph, and we will start the section about 0 and 1 spectrum criteria. So pause. Okay, so as I said, up to under this assumption, which was the assumption of theorem 810, we can write the positive and negative evaluation map there is an equality for one to the other with this epsilon as multiplicative constant. And so you can label the TP up to the following equivalence relation of the edge. So in fact, this can be depicted. Remember that the edge in the reference pattern we explained correspond to some evaluation map. And so we define the TP up to the following equivalence relation. Equivalence. I don't know, equivalence relation, maybe. I'm not sure. Up to the following equality, maybe equality, but up to the following equality. On the edge. On the edge. So, like that, equal epsilon I, like that. And maybe I forgot. Did I forget to put something here? Let me check something. I'm not sure. No, maybe not. Maybe not, because this depends on the definition on plus and minus. So it should be okay like that. And I wrote here really equality, the following equality. I don't know why I wrote equivalence relation. Okay, following equality on the edge. Okay. Quality. Where is it? Page. Okay. So now I will write that the categorical dimension is a character according to a result in EGNO book, and the sphericality is equivalent to the dimension of X equal dimension of X star for all simple objects. So lastly, according to EGNO book proposition 4, 7, 12, we may assume that the dimension function is a character. Dimension function, so like that, is so simplified like that. Of course, here you represent the simple object by the index. So you should write like that, X, if you want to be correct. Is a character of the fusion ring. and the relation di star equals di ensure sphericality as explained in section 2. More precisely, remark 212. Okay. So we are done with this section 12. So let us start section 13 about zero spectrum criteria. So this is the second criterion we mentioned in the introduction part. Remember that in our classification of unitary simple integral fusion category, we classified fusion rings and we excluded them using the quantum Fourier analysis. But under the bound we choose in the paper, it remains two fusion rings we cannot exclude from unitary categorification by quantum Fourier analysis. And these two, remember that the one called F210 was excluded by localization strategy. So the TP system taken as a, anyway, localization strategy. And the second one was excluded by zero spectrum criterion. So now we'll explain what is the zero spectrum criterion. We'll explain and prove it. And in fact, there is another criterion which has no application, which is not necessary for our classification of unitary simple integral fusion category in this paper, which is called the one spectrum criteria. We will explain both, and we will explain that they are not equivalent, and that there is no one which is stronger than the other. There are two criteria deserving to be explained. So, okay. Okay. So in this section, we will keep the notation from section 11. So as I said, the section 12 can be considered as the we don't use section 12 in section 13. And we don't also use the annotation, so we keep the notation from section 11. So this section keep the notation from section 11. It should be more or less the notation I recalled yesterday. This does not matter. Or no. Yeah. Section 11 was section 11 was the section called the Pentagon Equation. Pentagon Equation section. So section dedicated to the Pentagon Equation. And we assume also, this section assume that x double star equal x. For all objects, x. Okay. So which induces, so as we already know, a bijection from I to I star for the index of the simple object on I such that xi star equal xi star. So at the fusion ring level, such thing is automatic because at the fusion ring level, you have this bijection. But when you are at the categorical level, you should assume. But if you categorize, yeah, anyway. Okay, so we will simplify a bit the notation of the evaluation and co-evaluation map. So the morphism evaluation and co-evaluation map will be denoted as follows. So it's a very small simplification because in fact this section will meet some computation and it will be more comfortable to denote the evaluation and co-evaluation map as follow, but yeah, it's not essential, respectively. Okay. Okay. So now, what's the point of spectrum? What is a spectrum? So we will state and prove a categorification criterion, and this is called spectrum, 0 or 1 spectrum. So what is spectrum? And we will explain, we will define the spectrum now. And in fact, the definition of the spectrum involves the equation 13 and 14 in section 11 about the F symbol and the Pentagon equation. So let me maybe copy and paste the thing here. So it should not be very far. So 13, 14. Yeah. It will be more convenient. So let me put it here. I will make it small. I will use it. So this one and this one. Here. Okay. I put it in small. Okay, so define the spectrum. So by equation 13, a right-hand side summand of the Pentagon equation 14 is non-zero only when I0 is in. So I will explain. In this set, so I in I, such that n I4, I7, n I5 star, I8, and n I6, I9 star, I are positive. This set is called the spectrum. Where should I put this? So maybe I will put this here. Put this here in very small, just to like that. Then you don't need to come back like that. Okay. Or I don't know, maybe better to do that. So one here, and one here. Like that. Anyway. So that. So 13, 14. Okay. Okay. So this set is a spectrum of this equation. This specific equation, not the spectrum of the system, but this single equation. So why? So the right summand of that is non-zero only when I0, which is written here, I0, 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 is in this set. Why this is true? Because otherwise, so look at so I4, I7, I0. I4, I7, I0. So here, I0, I4, I7. So it corresponds to I0 here is I6. So I6 is here. And I4, I7 correspond to I2, I4, this one. So you see, as it is defined here, this right-hand side here is non-zero. If this is non-zero, this is non-zero, and this is non-zero. But as it is defined, this is non-zero when? So only if this is non-zero. So we need, no, the point is that we need this morphism here. A necessary condition is that this morphism exists, is non-zero. Which means the existence of such a morphism require this to be positive because this is a dimension of the home space in which this morphism is. So this morphism is in some home space, and this is a dimension of this home space. If the dimension is 0, then this morphism is 0, and then this coefficient is 0, and this is 0, 0, 0. So this corresponds to this corresponds to this corresponds to this. So I realized that I should maybe specify something. I guess, yeah. In the definition of the F symbol, I should specify that the definition is specified that all the morphisms are non-zero. What I should write also is that if one is 0, then it should be 0. So, if I remember properly, the definition of the F symbol involving this picture, we said that let mu1, mu2, mu3, mu4 be non-zero morphism, etc. You can extend the definition for 0 morphism, and then you just say that it is a 0 F symbol. Extend definition of F symbol equals 0 for with 0 morphism. Okay. Anyway, so the morphism is non-zero, like that, like that, like that. We need the home space to be non-zero. And okay, so the right summand, only when. So you have this right summand here, and we only need to consider you have the right hand side, and we only need to consider the summand which are non-zero. If it is 0, you don't need to consider this. You can specify I0 is in IS. Where S is I don't know the meaning of S for spectrum, maybe. So there is nothing called S only. So maybe it's just the name of the. You have I and I spectrum, S for spectrum, maybe. Anyway, so you can specify I0 in IS. This is the same thing because if I0 is out of IS, then it is 0, and it's okay. And this IS is the spectrum, so called the spectrum of this PE. And when I say this PE, I mean this single equation, not the full system. Not the full system. Okay. We have our definition of spectrum. Now, what do we mean by 0 and 1 spectrum? In fact, 0 and 1 will be the cardinal of this set. So we consider the cardinal IS of IS as measuring the complexity of this equation. So this number measures a kind of complexity for this equation. As measuring a complexity for this equation. Remember that in the localization strategy, one point of the strategy was we want to order the equation by complexity. And so there are several kinds of complexities, but one kind of this is the cardinal of the spectrum. You can define several other kinds. So the number of variables, I don't know. But the spectrum is one kind. So we will give two categorification criteria. One, when the cardinal is equal to 0, which will be called the zero spectrum criterion, and one when the cardinal is 1, which will be called the one spectrum criterion. So which we will give two categorification criteria with the one, the cardinal equals 0, corresponding to the existence. So here it's a bit confusing. What corresponds is not the fact that equals 0 do not correspond. What corresponds is the criteria. So we give two categorification criteria corresponding to the existence and one is like that and the other is like that. So what I mean is that this is not equivalent to what I will write here. You can do like that, but like that is so what corresponds is the criteria corresponding to the existence of an equation of the form x. So maybe I should rewrite because otherwise it's confusing. So two categorification criteria correspond one corresponding to the existence of an equation of the form x, y equals 0, x and y different from 0. Where is equals 0, so called the zero spectrum criterion. One, corresponding to the existence of an equation of the form 0 equal x, y, z, with x, y, z different from 0. So it can look a bit weird to say x, y equals 0 with x and y different from 0. But it's, in fact, this is the point. If you can isolate an equation, a Pentagon equation of this form, of the form x, y equals 0 with x and y equal different from 0, then it's a contradiction. So you have an equation without solution. And so the fusion ring is excluded from categorification automatically from this single equation. And in fact, This is so strong that it is excluded from any categorification for any field and any adjective. I don't know, spherical, pivotal, etc. It's excluded from any categorification. This is very strong. But you can say, okay, how you can find such a Pentagon equation? But this is very rare, but this exists. In fact, we will explain a way to reformulate such a weird equation that we will reformulate the existence of a Pentagon equation of this form in terms of the fusion coefficient. Okay. So here, where is equal 1, the one spectrum criterion. One spectrum criterion. So here is equals 0 because the right hand side. So I0 is in IS, but the cardinal of IS is 0. So the right hand side is 0. So you have something with a 0 right hand side. And you have this on the left hand side. That is why this implies this, but the converse is not true. You can have this equals 0, but on the left hand side, you can have something more complicated. That's why my previous formulation was a bit confusing. And here the same, the right hand side, you have one component, so one component. And you have an additional assumption here, which is not implied like that, of course. So it is yes, reformulation. Okay. Now, let me recall a bit the notation, some notations. So we will consider. So I recall something I already mentioned before, the usual bijection alpha prime from Bijk. So if you remember, this is the home space of morphism between xi tensor xj to xk. And so bijection between this space, this set, to this space, to its dual basis in okay, sorry. So this is a basis of that. Basis of basis. So wait. Basis of so to its dual basis in to its dual basis in home C xk xi xj. Okay. Given by the usual bilinear form from section 3, given by the bilinear form in section 3, more precisely in lemma 3.2. After, so it's not exactly, the basis of that is not exactly the dual basis of that. We need to apply some natural isomorphism, natural adjunction isomorphism, but it's essentially the same thing. After some natural adjunction isomorphism. Adjunction isomorphism. So as usual, I mentioned EGNO book proposition 2.10.8. I don't remember how many times I mentioned that. Anyway, so let me state the first lemma. And we will have no time to prove it. It will be proved next week. The first lemma, the lemma which will be used to prove the spectrum criteria. So lemma, so it's a lemma to force this lemma. It's you have an assumption involving the fusion coefficient to force the F symbol to be non-zero. And this lemma will be proved by using one-dimensionality. So this assumption can be reformulated into the fact that some home space are one-dimensional. So that's why this lemma is called one-dimensional trick. Lemma 13.2, one-dimensional trick. So this kind of lemma, in fact, so is used here, but this trick is, I guess, should be very useful in general in this theory. So it is applied here to prove the spectrum criteria, but in fact, this trick, so it's not completely, the proof is not so easy, at least it's not so short. The proof, I need 3 pages to prove that. So it's not trivial, but it's elementary. The statement is elementary. So consider, so it may have some other application than just the application for the spectrum criteria. It should be a kind of fundamental lemma. So consider non-zero morphism mu1 in the basis I2, this basis, mu2 in this basis, I3, I4, I5, mu3 in basis I2, I4, I6, and mu4 in this basis. So you consider 4 morphisms, sorry, in this 4 basis. Okay. Now, if you have the following, assumption on the fusion coefficient. Sum for k in I of n I1, I2, k, n, I5, I4 star, k, equal 1. Or, and this, we will state 3 equality like that, and this can be reformulated as the fact that some Hom space of this dimension is of, in fact, one dimensional. This is the dimension of the Hom space of xi1 tensor xi2 to xi5 tensor xi4 star. So this is the dimension, and we will assume it is one dimension. This is one-dimensional trick. So, or sum for k n I1 star I3 k n, so this fusion coefficient for star k equal 1, or again sum k n I3 I2 star k n I5 I6 star k equal 1, then the following, then the usual this F symbol, so the generic F symbol like that, for this specific morphism is non-zero. So you have, so you pick non-zero morphism like that, and you assume that one of these equality hold. So one of this corresponding Hom space is one dimensional. You don't need the third. You don't need the three. You only need one. Then you can deduce that this F symbol is non-zero. Of course, as we said before, if one of the morphism here is 0, then this is 0. But the converse is not true. You can have all non-zero, but still this to be equal 0. This assumption forces this to be non-zero. And the proof will be next week. End of session. The proof will not be, is not trivial. I can say it's straightforward. It's a bit long, it's 3 pages, so it's long, straightforward, but not trivial. Okay, stop here.